Hello everybody, and welcome to our next video, which is we're going to look at explaining TCP operations. And this is going to be one of those videos where you're going to go, oh boy. No, I'm just messing with you. The idea behind the different features that come into operations of TCP operations and things like that are going to play a kind of a vital role when we get into how this stuff actually works. So we're going to talk about path Mtu Discovery and what that is, the maximum segment size, and latency, fiber optic options and satellite transmissions and how latency is affected by those, windowing, bandwidth delay product, and global synchronization. And we're going to touch very lightly on the options, which we've already pretty much discussed inside of IP operations. But TCP, as you know, is also a three-way handshake. And what a three-way handshake basically does, and you've got a computer. That's a very large computer. Got a computer and you have a computer. You're going to have three-way communication. You're going to have the SYN. I want to form a relationship with you. This guy's going to send a response back. This is going to be most people refer to as a SYNAC. I want to form a relationship with you, and I acknowledge your synchronization. This guy's going to send a response back, which is also going to be a SYN and an ACK. Now this is a three-way handshake. If this guy right here doesn't form, then it's known as a two-way handshake, which doesn't actually exist. It's also what they call an embryonic or a half open, but we discussed that in the previous video. It's not something you want to have happen. Typically, you're going to see RST or resets when you have those because of the fact that it's an partially open TCP session, and the server is going to want to close that. So, the idea is actually very, very simple. You have a situation where you're sending traffic back and forth with the server. You have an open connection. If you were to do actually, let me do it this way. Go to CMD, and we're going to type in, let's bring this down just a little bit so you guys can see it. I'm going to do a netstat -network open and established. So I'm going to scroll up here just a little bit here and show you some things. So basically what you got going on here is you've got my computer talking to several other computers. I have a bunch of established connections because I do have a open web connection behind the scenes. You guys don't see it. But then we also have some local connections. We have some connections that I have for some loopbacks that are GNS3 related for me to use my home computer to connect into GNS3. Anything that you see down here that's : and an IP address, this is all IPv6. But if you notice, I have a bunch of TCP connections open. I don't have any, and there's a bunch of UDP down here as well. But if you notice, most of it isn't functional. So none of it's open. So I have all these connections going everywhere else. I like this because if it doesn't give my public IP address, it just gives the local IP address on my system. As you can tell, not many are open. I do have a open connection to my Windows Server 2008 R2 box, where this is my connection to him, and I'm remote desktop into him, which I could do that. And I also have another connection up here, which is 445, which, what is 445? Windows Domain Services, if you didn't know that. So that's what that port is. This right here is how TCP works. If you have an established, that means that the three-way handshake is good. If you have a time wait, that means that there's something wrong with it. Just wanted to show you guys how that worked. Now, path Mtu Discovery was actually a very good idea behind the way that things work. And what basically this does is it's a way for end-to-end connectivity to figure out how big something can be, how big of a MTU you can forward to a destination. And the reason that they did this was the fact of the way that the media has changed over the course of time. So by looking at this and reading what I have written down here, it's actually very simple. If you're trying to send traffic from point A to point B, and there might be a couple of different routers in between here to get traffic to draw another one right there. So we have 5 routers. Each one of these might be a different type of media. So you might have, fiber here, Ethernet here, serial here, Ethernet here. So regardless of whatever the media is, the MTU is going to be affected by it no matter where you go. So in Ethernet 1500, if you're using FastD, fiber optic, it might have a much larger MTU capability. So what you're going to do is, for IPv4 packets, what you're actually going to do is you're going to works by setting a DF bit, or do not fragment option bit, in the IP header. Then any device along the path whose MTU is smaller than that packet will drop it and send back an ICMP fragmentation needed type 3 code 4 message containing its MTU. So if we have traffic going to router 3 and it's trying to go to router 4, and it gets in here, router 4's MTU is not 1500, let's say it's 1380 or whatever. It's going to send that message all the way back to this guy, and that MTU is going to have to get lowered down to whatever this guy's MTU is. If it's 1380, that means the sending MTU now is 1380. He's able to pass through to the destination. That's the idea behind that. Mtu Discovery is good and bad at the same point in time. It's got some security vulnerabilities. So let me actually, that's the next paragraph. So we have many network security devices block ICMP messages for perceived security benefits. So you may not want to give out what your MTU is, but you might not have a choice. So depending on what's going on, most ISPs block this because they don't want to send this through. But in case that you do receive this message, that's what it's telling you. It's telling you that there is an issue somewhere and you need to modify your MTU. That's basically what it is. So moving on to MSS, maximum segment size, is a parameter of the TCP protocol that specifies the largest amount of data specified in octets that a computer or communication device can receive in a single TCP segment. It does not include the TCP header or the IP header. The IP datagram containing a TCP segment may be self-contained within a single packet. So the maximum segment size is used to avoid fragmentation. It is equal to the largest datagram size that any host is required to be able to reassemble minus the IP header and TCP header size. So it actually gives you an example of right here. 1220 in octets, 1280 minus 40 minus 20. So TCP header and IP header. Where we talked about that. The MSS is going to be 1280. So you're taking 1280 minus 60 is 1220. So that's the idea. A lower MSS will ensure the fragmentation will never occur along the path, but will result in higher overhead. So for most computer users, the MSS is established by the operating system on the SYN packet during the TCP handshake. Each direction of data flow can use a different MSS. So that's important for you to remember. So that's why I mentioned it. That's why I drew this out real quick when we first started and how this works. So this guy his MSS might be 1480. This guy's might be 1260, or whatever the case may be. So that just gives you an idea of what's going on. Now latency, kind of a big topic, and latency and windowing and bandwidth delay product and global synchronization too. But more effectively, bandwidth delay product and windowing can all kind of roll into one big pie of things you don't want to have to play with or deal with. But latency is common in packet switch networks. The time is measured either one way or round trip delay. So one way is the time from the source sending a packet to the destination receiving it, or round trip delay, one-way latency from the source to the destination plus the one-way latency from the destination back to the source. Now, if you were to do a ping and you get the 5 exclamation points, you're going to get you're going to get some response times. So they'll usually be in brackets, and you're going to get 27 milliseconds, so on and so forth. Trace routes do the same thing. What they'll do is they'll give you a low, medium, and high value for each they'll give you a low, medium, and high response for each hop along the path. So the idea behind latency is to determine how much latency. And realistically, latency is going to be, there's going to be latency regardless of how you build your network or how much bandwidth capabilities you have or whatever the case may be. If you have traffic going from point A to point B, there's going to be a couple different types of delay that are associated with latency. Now, delay is the time from point A to point B. There's a variable delay, which is going to be things like voice over IP traffic. They're very sensitive to delay. And then we have fixed delay, which is the propagation delay, which is how long it takes for a packet to be in transit. These things right here are going to be something that you cannot really account for or really play with. It's going to be what it is, regardless of what you do to try to fix it. So propagation delay and variable delay are going to be things that you're not going to have a whole lot of control over, because it's going to take time for data to go from one device to another device, whether it's 4 feet away they're 4 feet away from each other, or if they're 4,000 miles. It doesn't matter. There's going to be a propagation delay. So pings and trace routes are going to be able to tell you what's going on. You might also look at some other things like round trip times and things like that. But at the end of the day, that's what latency is going to be. It's actually very, very simple to define. Now, fiber optics and satellite transmissions, when they come into play, fiber optics are really, really fast. It uses light, so it's really, really quick. But that's pretty much what it boils down to. Is you're going to have latency, and if you can, I think I didn't do it in this one. When I get into bandwidth delay product, we'll talk about that a little bit, and that'll give you an idea of what's going on a little bit more. Now, windowing and global synchronization have a lot to do with each other. Now, windowing is actually very simple. It's the technique used by TCP, the method of controlling the flow of packets between two computers or network hosts. TCP requires that all transmitted data be acknowledged by the receiving host. Sliding windows is a method by which multiple packets of data can be affirmed with a single acknowledgement. So TCP includes a memory buffer, and that sits between the upper layer application layer, for example HTTP or FTP, and a lower layer that receives it, so the data link. The buffer allows TCP to receive and process data independently of the upper layer application. TCP can use this buffer space to read ahead, while the upper layer application processes the data at its own pace. So now let's talk about bandwidth delay product for a moment, and then that'll global synchronization, and that'll kind of fill in some gaps here. So global synchronization can happen when TCP/IP flows experience congestion, because the sender will reduce their transmission rates at the same time when packet loss occurs. So you'll actually get a situation like this, where you have a maximum forwarding rate, and you have this right here, and then it'll start dropping off, and it'll come back up again, and then it'll drop again. This is what they call global synchronization. It gets into a flow, if you will, of how fast it can send traffic and things like that. So the idea is to prevent this with a thing called random early detection or weighted random early detection. And what this does, it's a queuing. It is a quality of service mechanism designed as congestion avoidance. You have, and I've talked about this in a VMware video, but you have congestion. You have congestion avoidance and management. Avoidance is weighted random early detection. Management is queuing, and then you have policing, which is going to be I cannot spell today. out in traffic, and then you have shaping, which is outbound. I know I just almost drew out, or in, I'm sorry. But the idea behind global synchronization is to prevent traffic that's going to bottleneck an interface and then have that all this traffic right here not being able to forward. This is all wasted bandwidth right here. So whenever you have wasted bandwidth, you're going to want to take care of that. So by utilizing random relay detection, which is going to randomly drop packets, or weighted random relay detection, which you can set a precedence to what packets are going to be what. So you might have voice over IP might have the best forwarding possibility, and say for instance web may have the scavenger, or whatever's left over web will get, because you don't want your users surfing the web all day. What you could very easily do with random relay detection, especially weighted random relay detection, is you could set scavenger class. So you could set a class map and set a policy that WRED will drop web traffic if it starts to see that it's starting to increase the latency on the interface. You could use weighted random relay detection to drop web traffic, and instead of having a situation like this, you have a situation like this, where traffic is sent at a pretty consistent speed. There might be some drops here along the line, but you're going to have it at a much higher rate for a much longer period of time, which is going to give you a better forwarding capability. Now let me come back up here to bandwidth delay product. Now bandwidth delay product basically refers to the product of a link's capacity in bits per second and its end-to-end delay in seconds. So the result, an amount of data measured in bytes, is equivalent to the maximum amount of data on the network at any given time. So what that basically means is you might have a very, very high bandwidth link with very, very high delay. Satellite connectivity is very common for this. A network with very large bandwidth delay product is commonly known as a long fat network, or LFN, or an elephant. As defined in RFC 1072, a network is considered LFN if its bandwidth product is significantly larger than 10 to the 5th power in bits, or 12,500 bytes. So ultra high speed LANs might fall into this category, where protocol tuning is critical for achieving peak throughput. So it's one of those things where if you've dealt with it, you know what I'm talking about. If you haven't dealt with it, you're gonna wonder why your 10 gig connections between your switches are gobbed down, and you're not sure why there's so much delay on the link, but there is. So you can see this sometimes with and satellite is obvious for one, because there's such a long period of time that the data is going to be in transit is going to be one. But that's the idea behind how most of this stuff works. I mean, it's not really too complicated, but as I mentioned a minute ago with the way the global synchronization works, that's where windowing comes into play. And latency. I mean, latency is kind of a killer on networks. Now, the fun part isn't knowing what each one of these is. It's trying to figure out where in the network this stuff is occurring and trying to figure out what is making it do that. There's ways that you can do this. So SolarWinds Orion is a good place to start, because then you can start looking at drop packets and stuff like that. You could do some sort of embedded event manager where you have so many drops in a certain period of time will trigger an update or trigger a SNMP trap. There's several different tools you can use. I personally like to use NBAR when I'm going through and doing classification, because then I can go in and I can tell a particular device I want to know what type of traffic is traversing. So if you don't have QoS working in your network, you can go ahead and implement NBAR, network-based application recognition. It's usually at the interface level, and you type in, for the Cisco device, you would type in at the interface level IP NBAR protocol discovery, and you would hit enter. That would turn on NBAR at on the interface, and you could then go down to privilege mode or enable and type in show IP nbar protocol discovery and hit enter. It's going to show you what type of traffic is going through your network and how many packets and how many bytes. And the bigger numbers obviously mean more traffic, so you can look at it from that perspective and see exactly what's going on. Cisco has this thing called a PDLM, which stands for a Packet Database Language Module, I think is what it stands for. And it's a way for the router to be able to identify traffic and be able to tell you what it is. So where I work currently, we have NetFlow enabled on all of our WAN routers. So we're using NetFlow. We have a SolarWinds server, and I set up NetFlow, and the SolarWinds server is gathering the NetFlow information from the routers. I implemented nbar on all the interfaces that needed to be forwarding traffic, and we updated the PDLMs with our service account, and we were able to go through and, based on the PDLM output, we were able to determine what type of traffic is being forwarded, and then from there we were able to write different QoS markings and policy maps and things like that to remedy why we were having latency in different areas, give priority to some traffic, take other priorities away from traffic that had priority that didn't need it, things like that. So there's ways you can play with your traffic and be able to manipulate it. Traffic engineering, in the simplest terms, is being able to go in and manipulate the traffic based on a set of circumstances. Well, that's kind of a loaded question, because if you don't understand what circumstances you're trying to remedy, that's going to be the hard part. So if you see a lot of latency, you may want to go in there and figure out why you're getting so much latency. Is it ping? Is it application? What is it that's causing all of these issues? So at the end of the day, it's your job to figure that out. So I just gave you a real-world example as to how that actually comes into play. It's not the only one, but it's one that I realized, and I go, well, there's got to be a simple way to figure this stuff out. And I think a 5-minute Google search led me in the right direction. Actually, it led me back to Cisco's Learning Network, and somebody was having the same problem. I already had nbar working. I already had NetFlow working. It was just a matter of updating the database that nbar went out and referenced traffic against, because it's going to see what type of traffic it is. If it doesn't have a database to reference the traffic against, so if it doesn't say, okay, I see traffic type AXY1, and it doesn't have a database to compare that to figure out what AXY1 is actually forwarding, it's going to have to figure that out. So the PDLM was great, because then we were able to say, oh, that's Citrix traffic. So we want to give that precedence. And then we found out that traffic type 1B31 was BitTorrent, because we gave somebody local admin rights. They downloaded BitTorrent and they were downloading music because we told them they couldn't stream music. So they were able to go in there and download music to their computer and play it, and they were downloading albums at a time. So we were able to go in there and police that down to 10K per second. And so then we got a complaint that, and that's the funny thing about users sometimes, they'll be doing something that they shouldn't be doing, they'll do something they know they shouldn't be doing, and then when we go in there and we tell them, we create a QoS policy that slows that traffic down, then they put in a ticket because of the fact of they can't download music anymore, even though they were never supposed to be able to download music, period. See how that kind of works, and it's weird that users do what they do, but it is what it is. So if you're a user and you're doing something you're not supposed to be able to, or you shouldn't be doing, the administrators probably know about it, and it's just a matter of time before something happens. So usually when I see stuff, I pass it off to my boss, and he goes out and he does what he has to do. That's just kind of his thing. I've never been one to go ream a user because they keep locking themselves out. It's my job as the administrator to keep people working. So that's the idea. Administrators aren't out there to take your head off if you accidentally delete a file. Administrators are there to make sure that you can do your job. So, or your friend. Just be aware of that. So, and enough of me ranting on about different things. You guys obviously get what's going on here. If you have any questions, feel free to drop me an email. If you would like this OneNote document, please let me know. I'm more than happy to send it to you via email or through Dropbox or whatever the case may be. I hope this has been informative for you. I want to thank you for viewing.